Alright, in this video we're going to be focusing on how to find the domain of the function algebraically. So we are finding domain algebraically. Alright, so before we get to that, I just want to remind us of what the definition of domain and range are. So the domain is the set of all possible x values which will work in the function. Of course, work is not a mathematical term, so which will work in the function. And these will output real y values. And so these we're going to be able to find by hand, and in this class I'm going to typically show you, actually for this unit we're always going to be finding these by hand. So you'll be able to verify your answer on a calculator often, but these are going to be by hand primarily. For the range, this is the set of all possible y values. Of a function that result do you like that LT and it looks terrible? That result when we substitute all of the possible x values into the function. So the set of all possible y values of a function that result when we substitute all of the possible x values into the function. So I liked these definitions. I stole them from another teacher, and I like them because I think if you forget what you're doing, if you go back to this definition, you should be able to think your way through it. So these are they help you work through the common sense of the math. So when we do range, we're typically going to actually do this in the calculator to keep your lives a little bit easier. All right. So there are two functions that you guys have looked at in your earlier math classes that have limited domains, and those are the ones that we're going to be focusing on that help us find the domain by hand. So the first one is rational functions, and like the most simplified version of that would be f of x equals 1 over x. And if you guys remember, we can't have 0 on the bottom of a fraction, so if I was to write the domain for this, there's a few different ways I could write it. I could say all real numbers except for 0. I can't have 0, but I can have anything else I want. If you were writing it, and that would be the set notation. Another version of set notation would be x is less than 0 or x is greater than 0. So that would work for set notation as well. And then interval notation would be negative infinity to 0. And then 0 to infinity, so just saying that you're skipping 0. So lots of ways of writing the exact same thing. The other function that you've seen in the past that has a limited domain is radical functions. So the most simple version of that would be the square root of x. And if you guys know here, you can take the square root of 0, and you can take the square root of positive numbers, but you can't take the square root of negative numbers with getting real y's. You can get imaginary y's, but you can't get real ones. So here we're going to say that the domain is x is greater than or equal to 0, and that's set notation, or in interval notation you would say 0 to infinity, like that. So when we look at problems, we're going to see what part of it is rational and what part of it is a radical, and then we're always going to refer back to these ideas to see what we're not allowed to have. All right, so our first example is going to be f of x equals x plus 3 on the top and x squared minus 5x plus 6 on the bottom. So if you compare this with the two above, then we're looking at rational equations, which means what we're focusing on is what would make the denominator equal 0. And whatever it is that makes it equal 0, that's what I cannot have. So if I want to know what makes the denominator equal 0, it kind of helps to take the denominator and set it equal to 0. And if you guys remember how to factor, these are simple simple quadratics to factor. So we're looking for two numbers that are going to multiply to a positive 6, but add to a negative 5. And the two numbers that would do that would be negative 3 and negative 2. And then once it's in factored form, we would say x equals 3 and x equals 2. So when we look at this, the two values that would make the bottom equal 0 are 3 and 2. And so those are the two values we do not want to have. So once I found them, I'm going to say I can't equal 3 and I can't equal 2. All right. So now for the domain, we have a couple different ways to write it. We can say all real numbers, x can't equal 2 and x can't equal 3. Or we can picture this as like being on a number line, so we have all the numbers that are less than 2, we can have those. Or we can have the numbers between 2 and 3. Or we can have the numbers bigger than 3. So this is set notation for both of those. And then if you did interval notation, you would say negative infinity to 2, 2 to 3, 3 to infinity. All right, for the next example, we're going to say f of x equals the square root of x plus 3. So, of course, this is the one with the radical, so if we look back to what we know about radicals, we have a whole range of numbers for our domain that are going to work. So we're just making sure that whatever is underneath the radical is not negative anyway. So what we're going to do is we're going to take what's underneath the radical and we're going to say the stuff that's underneath the radical has to be greater than or equal to 0. And then we have to solve for that x. So I subtract the 3 over, so x is greater than or equal to negative 3. That was pretty easy, we're all done with that one. So for my domain, I have x is greater than or equal to negative 3, and I can write that as negative 3 to infinity also. All right. Now, before we move on, I do want to take a second and look back at these two problems, because we're going to try a more complicated one, but I want to look at these first. And just see what we're noticing from the graphs about the range specifically. So on this one, we're going to go ahead and graph it. And I'm going to plug it in as a fraction because I can. So x plus 3 on the top, and x squared minus 5x plus 6 on the bottom. If your calculator doesn't do that, then you should put x plus 3 in parentheses, divided by, and then the whole bottom in parentheses. Minus 5x plus 6, like that. That's what you should be doing. I'm going to clear that so that it doesn't do anything. All right. So if I graph this, and I forgot I changed, bear with me, I forgot I changed my window and made it huge. If you look at this, we're just trying to double check and look at the y values that correspond to all the x values that we have. So if you look here, I can see that nothing is getting lower than 0, it looks like. So just by looking at the graph, I'm thinking, okay, maybe this is y is greater than 0. Kind of looks like there's an asymptote there. Kind of a cheater way to check. A lot of these, if you choose any of these, it kind of traces the graph. So what I usually do is I'm not actually trying to find the x-intercept here. I'm just kind of scrolling along. I'm noticing, and it did cross over. It did cross over the y-axis there. The video, because I had an answer for this that wasn't right that I realized as I was making the video. So, and that makes sense where I said it crosses over the y-axis. That makes sense because if we look at the equation,